In this video series, we'll be taking a look at some of the key concepts of utility network management for ArcGIS, Esri's long-term GIS solution for network management for a modern utility. In this presentation, we'll look at aspects of the information model for data and network management. I'm Aaron Sapsford, GIS Utilities Practice Lead at Eagle Technology based in Wellington. Okay, so this diagram is a top-down look at the information model. The domain network is what your commodity is carried through. So this is your connected power, water, gas, or your telco network. Your domain network can then be further defined into tiers, like partition tiers in an electric network, which are sequential in nature, so you can model generation, transmission, distribution, and low voltage. Or in a water or gas pressure network, you could then have a hierarchical system of tiers and tier groups, which can contain distinct pressure and isolation zones. Subnetworks are created to support trace analytics. So a subnetwork is the analog of an electric or circuit or feeder, or a water district metered area with differing isolation zones. So there are 5 feature classes that locate and describe your network assets, and these are then further defined through combinations of asset groups and asset types, which we'll go into shortly. There are also 3 feature classes which represent your structure network, points, lines and polygons, which support your domain network. Included behind the scenes are other tables which hold information about terminal configurations for devices. There are also business rules which describe how each of your features in your network interact with each other. Tables to store information about your schematic diagrams and how they're laid out for later sharing. And your topology, which puts it all together to help keep your network valid and connected. There's also support for non-spatial features coming very shortly to the utility network. So non-spatial features are a way of representing things like ports, splice points, buffer tubes, and fiber connectivity in a telecom network. Okay, so to break each area down, we're going to go through some of these key terms, concepts, with some explanations. In a utility network, operational networks are expressed as domains. So this is the commodity that your utility business delivers. To understand some of the key data concepts, we'll first take a look at asset packages. So an asset package is a particular flavor of file geodatabase, which is designed for each of your industry's domain network requirements. Because an asset package is a file geodatabase, it essentially is portable and disposable, and this is where you'll take your first look at the data model, and ultimately where you'll stage your GIS data before deploying it to your enterprise. The asset package is where you will define your features, subtypes, domains, and other operational and business attribution that you may have. There's also a collection of other metatables contained in an asset package that define how your network will behave. So these are things like your business rules for connectivity, attachment and containment, and some schematic diagram templates to get you started. Esri provide utility network foundation solution templates with pre-canned asset packages for each industry domain that you can configure to suit your own needs. They do have pre-populated sample data for Naperville, so if you want to take a look at a sample network, see how it behaves, then you can. They're intended to be changed, and this is by design, so the templates don't limit you to what you can do with your data modeling. If you want to check these out, go to solutions.arcgis.com. The service territory is a polygon feature that you will need to create your utility network. It defines the maintenance extent of your network, and it's Z and M enabled to support your network in the 3rd dimension, or if you want to interpolate measures along your linear features. The structure network defines what carries or supports your domain network. These are designed to be leveraged right across your network and can be shared by multiple domain networks like fiber optics and electric lines. So there are 3 feature classes for all structure networks. Structured junctions are the point features that can either be a structural feature to which a device is attached or a container of multiple devices. Structure lines are linear features that carry a resource. The structure lines can contain other structure lines that contain operational lines. So think of it as a trench with ducts that contain cables. Structure boundaries are polygons, and these contain other structures, devices, lines, and assemblies. So the structure network support associations for a structural attachment or containment. Your domain or operational network is determined by the type of data model being built. Now, this manages the operational part of the network which carries your commodity, whether it be power, water, or gas. The 5 feature classes or layers that are needed to create a domain network are devices. Now, devices are point features that are compact features through which your utility resource flows and affect the state or changes the flow of your resource in several ways. Devices can optionally have terminals where there are multiple distinct entry or exit points on a device. Junctions are also points. They're locations where lines connect to lines or lines connect to devices. These are connected but passive as distinct from devices which are active. Junctions are placed as needed mid-span or at the end of lines to complete the connections of all the features of your utility network. Lines, as the name suggests, are your linear features that deliver your commodity. So these are your pipes or your conductors. Lines can be connected to other lines via junctions or devices. They can also be contained in assemblies as well as structural features acting as containers. Assemblies are point features which represent a collection of other devices and junctions. Assemblies are designed to show a single point symbol on your map, but you can model other features and their connections. Subnetwork lines define the current extent of a resource. Now, this differs slightly from your normal lines as they aren't directly edited like other features in your domain network. For water or gas utilities, subnetwork could be generated for a specific pressure or isolation zone, or in an electric network, they could be a designated circuit or feeder. And because devices are switched often, subnetworks can frequently change, and they need to be generated on demand or post-processed after edit workflows have been completed. Subnetwork lines are used for tracing and can be configured to roll up totals like combined load or pressure, custom accounts, and the number of switchable or protective devices on your subnetwork. The asset group attribute represents the general classification of a feature. So the asset group is actually your feature class subtype in a structure network and domain network feature table. These are established to define the major classification of your assets. Asset types further refine your asset group categories into specific functional descriptions of your features. The asset type field is implemented as a set of attribute domains that are assigned at the subtype level for each asset group. For example, a transformer asset group of the device feature in an electric distribution domain network may have step, power, and distribution transformer asset types. Or for a line feature class in a water distribution network, service pipe asset group might have residential, commercial, and hydrant service asset types. With the utility network, you can model devices to a much higher degree of realism using terminals. You can optionally model these as specific ports on device features. Now, not all device features require the definition of terminals. If a device has 2 terminals that are equal or interchangeable, such as 2 sides of a switch or a valve, then you don't necessarily need to define these. There are some situations where they do need to be defined. And these would be where devices that serve as a subnetwork controller or source. Any device with 3 or more physical ports or points of connection, where 2 ports are distinctly different, so such as a high side and low side port on electric transformers. Devices with connection points that only allow flow in one direction, such as a check valve in a water system or network protector in an electric system. Terminals don't appear on the map. Rather, they're logical connection locations that control how other features can connect through valid paths. Tiers are a way to logically represent your network in segments. Tiers can be managed separately or grouped together, but they're still able to interact with each other. Tiers are named and can also be grouped. Partition networks are sequential, operationally separate but logically connected. For instance, an electric utility might want to have their high voltage or distribution network partitioned from the low voltage side. You'll still be able to propagate traces upstream or downstream across tiers. Hierarchical tiers would generally be used for mesh networks like water or gas distribution, where each are defined by certain properties such as different districts, pressure, or isolation zones. For domain networks with partition tier definitions, both radial and mesh topologies are supported. Partition tiers are sequential in nature, like electric and telco networks, and are independent from each other. So features within a tier will only participate in one subnetwork within that tier. Traces can be propagated across tiers as long as you define the target. So network traces will be covered in an upcoming demonstration video. Hierarchical tiers only support the mesh topology. So this allows you to model networks that can be nested, so each tier within the domain network are dependent on and inclusive of all subsequent tiers. So features inside a tier will participate in each higher tier. Tier groups can be used to model the different sections of those different types of networks. For example, in a gas network, gathering, transmission, distribution, and cathodic protection. If you manage or model only one sector, let's say it's only in distribution, then it's still a requirement that you create your domain network with at least one tier group. If you need additional sectors in your network, like say cathodic protection, you can add them later without significantly adjusting your network model. Tier groups are not used in partition networks like those used for electric or telco. Now, I've mentioned subnetworks a few times now, so to explain this a little further, we see a subnetwork as an even smaller subpart of your network inside a tier. So the example we often use is a subnetwork as an individual electric feeder or a specific isolation zone in a water network. The subnetwork is defined by the subnetwork name, which is unique and defined at the subnetwork controller at your source. So this would be a single device for a radial network or one or more for a mesh network. The subnetwork table holds a single record for each subnetwork in your utility, and the subnetwork line, which we talked about a few slides back, is created by a trace task on a validated network topology with no errors. The update subnetworks task stores a roll-up of your network properties on an aggregated line feature, which you're able to represent to your users in their maps so they're able to run traces. And this would generally happen after all of your edits are posted and validated as either a manual task, or this can be scripted to run as a maintenance task by your GIS admin. And subnetwork system diagrams can also be optionally created when your subnetwork lines are updated. Network diagrams are a representation of geographic information drawn using visualization techniques using pre-canned diagram algorithms. So these are commonly known as schematics. These are network diagrams, a way of showing a simplified representation of your network to explain the network structure and the way it operates. These can be created by your users as a quick way to show a logical view of sections of your network or the result of a network trace or a set of selected features. Now, these diagrams can be stored and edited and saved inside of the network and be made available and secured for views of complex or critical operational portions of your network, like a zone substation. There are a number of tools available in ArcGIS Pro to create your diagram layouts, and you can also edit white space and the way the orientation of your diagrams to suit your particular situation. Now, probably most importantly are the rules which govern your connectivity. An edge junction rule is the most simple, and this rule defines which point feature, asset group, and asset type combination can snap to which linear feature, asset group, and asset type combination. This is more or less the same way you would enforce a rule in a geometric network using coincidence. A junction-junction connectivity association is used to connect points to each other by implicit connectivity. Junction-junction connectivity rules manage this type of association. This connectivity rule type also supports the connection to terminals on device features, and you can define connectivity associations for device and junction feature classes in a domain network as long as the network rules exist to support the association. The edge junction edge rule type further defines how network elements can traverse intermediary devices or junctions. An example of this would be a main pipe connecting to a service pipe by a particular type of fitting. Containment associations enable the modeling of assemblies or complex devices in your network, while controlling map clutter, allowing for dense collections of features to be represented by a single feature on the map. Devices, junctions, and lines can be placed inside of objects like substations, switch cabinets, trenches, and ducts, and this improves visibility on the map and promotes better representation of your assets in your map products. So a polygon container defines a general area containing many features, like a substation or pump house. The linear containers can span some length, like a trench or duct bank, and these would normally contain multiple lines. A utility network supports nested containment as well. So in nested containment, a containment feature can contain another container feature. Gets confusing, which then in turn contains your network content. So like a substation can contain a junction box, and then the junction box contains a number of electric devices. Similar to structures and structural attachment, resources don't flow through containers, but traces can be configured to either include the contents of the container or just traverse across them. You can define structural attachment from devices, junctions, and assemblies in a domain network to structures in the structured junction feature class. So you can define a structural attachment from one structured junction to another. Point features can be directly attached to other point features, for example a transformer attached to a pole. Line features must have an intermediate attachment point attached to either an endpoint or to a midspan vertex. And you can define what features in your structure network support structural attachment associations by assigning the structure association role. Another example of structural attachment is a stormwater manhole access point inline to a pipe. This is useful when you trace your network but only want to return structures that are associated with the network when the resource doesn't traverse them. When assigning association roles, deletion semantics are configured to control the user experience when working with structural attachments. This controls the behavior of features when a structure is deleted. For example, you can specify the attachments that need to be removed or detached before you can delete the structure. Information inside your network topology is stored as binary pages. This allows things like tracing and diagram functions to read and process information about the network in a really efficient manner, as opposed to retrieving information directly from individual features in your network, as you would say in a geometric network trace task. Connectivity is defined by feature restrictions at the class level, then by network rules defined by valid asset group and asset type combinations. The network topology is enabled to allow normal network tasks like tracing, editing, validation, and error checking. When the topology is disabled, you're then able to perform administrative tasks like adding new rules or assigning association roles to assets. It's also recommended that when you're loading large amounts of data, leave the topology disabled, as it helps to reduce the overall processing time. Dirty areas are polygons which can be displayed to represent a part of the network that's changed or not yet been validated against the network topology. So any changes to geometry, attributes that define network properties, or associations can create dirty areas. Dirty areas are accessed in ArcGIS Pro in the Utility Network group layer. After a topology has been validated or enabled, errors can then be displayed for any network features that could cause you issues. Errors are generated to signal any issue with individual features, connectivity, or geometry, giving editors the opportunity to investigate what's potentially breaking any rules and to be able to fix them. Errors could also show up for any associations that are inconsistent when a network topology is validated. This is another way of ensuring your feature edits comply with your topology rules and make sure your data quality is much better. Some final words on the validation framework. All of your rules supporting a connectivity based on geometric coincidence are checked when the network topology is validated or enabled. After the topology has been validated or enabled, the system will generate errors for any network feature that is going to cause you issues. So the rules controlling associations are also checked when you try to create or import an association when a network topology is valid. But any error is generated on the feature only to indicate the association that is invalid. There is a reference list of all the topology errors and potential solutions available in the ArcGIS Pro help. There is a lot more information than I could have covered, but hopefully this gives you a good overview of some of the key terms and concepts. We also have some more utility network video content. We'll be looking at what you need to start thinking about when planning to migrate to the utility network. And we'll also be taking you through some more in-depth demonstrations and workflows with real data in a utility network, covering editing workflows, tracing, diagrams, and more. We are here to help, so if you need any more information or have questions about the content covered in this presentation, please contact us here at Eagle at the email address on screen, utilities@eagle.co.nz.